Okay, the last part of chapter 4 is going to be unsteady flow process, which is different from, the what we studied earlier. So we are going to use different governing equations, different mass balance equation, different energy balance equations. So this last problem may look slightly different from, the what we studied in the past. So unsteady flow process is what we studied in chapter 3. The most of the engineering and most of the energy balance equations in chapter 4 were steady state open systems. So steady state open systems, we assume that there's nothing change in time. So this from this original energy balance equation, the energy transfer in minus energy transfer out is the change of energy of a system. From this equation, when we had steady state, we neglected the right-hand side, which is a time-dependent term. What happened to the system before and after? So we moved this one to the right-hand side and said energy transfer in should be the same as energy transfer out. And we also divide each term by time and said the rate of energy transfer in should be the same as the rate of energy transfer out. So this was the energy balance equation that we studied in steady state open system. But now we are going to have an unsteady open system. In unsteady open system, we are not going to neglect the right-hand side. So we are going to use the right-hand side. So let's see how this energy balance equation is going to look like. So we have energy transfer in minus energy transfer out is going to be the change of energy of a system. To determine the change of energy of a system, you can think about the energy balance equation we used in chapter 3. The right-hand side of the energy balance equation we studied in chapter 3 was U2 minus U1 plus moving boundary work was the change of energy of a system. So since we have an unsteady open system, we are going to use the same right-hand side as the chapter 3. The left-hand side is the same as the previous, the chapter 4 materials. So we are going to consider heat transfer Q, energy transfer by work W, and energy transfer by mass, which is mass transfer in multiplied by its enthalpy, kinetic energy, and potential energy. And we have energy transfer out, which is going to be the same thing. Heat transfer Q, energy transfer by work W, and mass transfer that goes in. This one has enthalpy, kinetic energy, and potential energy. This is the same as U2 minus U1. If we use specific internal energy U instead of capital U, you can say mass times lowercase u. Since it is the final state, we are going to say M2 times U2 minus M1 times U1 plus moving boundary work. So this is the energy balance equation for an unsteady flow process. The main difference between the energy balance equation for steady state is that we are not going to use this rate form. So we are not going to divide each term by time because it is now time-dependent problems. Because of this right-hand side, we are not going to divide each term by time. Okay, so that's it. We are going to use this equation to solve any unsteady flow process. And let's talk about mass balance too, since we studied energy balance. Mass balance looks the same. We just need to replace this E with mass M. So M, mass transfer in. minus mass transfer out should be the same as the change of mass of the system. How do we determine the change of mass of the system? Think about the buffet story. If you want to measure, if you want to calculate the weight change of your body before and after entering a buffet, you can calculate the weight of your body after eating and measure the weight before eating. So M2 minus M1 is how we determine the change of the mass. It's going to be mass in minus mass out. So this is mass balance equation. So we have mass balance and energy balance. We are going to use these two governing equations to solve any problems in unsteady flow process. That is the theory. And let's solve this problem. We have an insulated vertical piston cylinder device. We have initially contains 10 kilograms of water. Okay, so 10 kilograms. So initial mass is 10 kilograms. M1 is the initial mass. Initial mass is 10 kilograms. And 6 kilogram of which is in the vapor phase. That means that we have a liquid and a vapor together, meaning it's that it is saturated mixture. Where can we use this information? To determine the properties of the initial state, the properties of the initial state, U1. By the way, M1 is 10 kilograms. And we can use this information to determine U1. So at state number 1, at the initial state, we know the 6 kilograms of which is in the vapor phase. So the quality X at the initial state can be determined by the mass of the vapor divided by the total mass, which is mass of the liquid plus mass of vapor. So you can say it is 0.6 because 6 kilograms of vapor out of 10 kilograms of water, right? So 0.6. The mass of the piston is such that it maintains a constant pressure process. Oh, so the pressure is going to be 200 kilopascal. P1 is 200 kilopascal. It maintains the constant pressure. So P2 is also 200 kilopascal. We have the steam entering the system at 0.4 megapascal, 360 degrees Celsius. So we can use this information to determine the properties at the inlet. What about the exit? There's no information about the exit. So we have an inlet, that's it. So we have inlet and that's it. There's no exit. So we can neglect everything on this side. And we usually neglect kinetic energy change, potential energy change. There is no information about work. So you can neglect energy transfer by work too. This one. And what about heat transfer? There's no information about heat transfer. Oh, you can see there's information. It is an insulated piston cylinder device. Insulated means there is no heat transfer. So you can also neglect this one. So what do we have? M in, H in is going to be M2 U2 minus M1 U1 plus moving boundary work. But this is a constant pressure process. Do you remember what is the right-hand side of this energy balance equation when we have a constant pressure process? Let me review, what we did in chapter 3. Yeah, what will be the WB? Right. So on the right-hand side, so let me rewrite this equation. So we have M in, H in, M2 U2 minus M1 U1 plus moving boundary work. So the equation is M in, H in is M2 U2 minus M1 U1 plus moving boundary work. If you have a constant pressure process, moving boundary work is going to be P V2 minus V1. And you may remember this one is U2, this one is U1, and you can combine. So since this one is PV2 minus PV1, you can also say P2V2, P1V1 because it's a constant pressure process. P1 is the same as P2. Then you can combine these two and say H2. You can combine these two and say H1. So this right-hand side becomes H2 minus H1. That can be determined by M2H2 minus M1H1, which was a chapter 3 material. Then the energy balance equation is going to be M in times H in is M2H2 minus M1H1. This is the energy balance equation. What about mass balance? We just wrote mass balance here. M in minus M out, but there is no M out. There was only one inlet, no exit. So M in is going to be M2 minus M1. So these are the governing equations. Okay. Now, going back to the problem. We know the initial mass is 10 kilograms. We have information about the initial condition. P1 is 200 kilopascal, X1 is 0.6. What about at the final state? At the final state, all the liquid in the cylinder has vaporized. So what is the phase change process after all the liquid in the mixture is vaporized? It's going to be saturated vapor. So after this process, P2 is going to be, since it's a constant pressure process, P2 is again 200 kilopascal, and it is phase change process number 4, saturated vapor. If you know you have a saturated vapor, you can determine its property easily. What about at the inlet? We have 0.4 megapascal, 360 degrees Celsius. So there is no information about the phase change process, but we can calculate that. P in at the inlet, 0.4 megapascal, and temperature at the inlet, 360 degrees Celsius. Then, what do we need? We need to determine the specific enthalpy at the inlet, at the initial condition, at the final condition. So let's do that. H1, H2, H in, these are what we need to determine. The first one is easy. It's a saturated mixture. If you have a saturated mixture, you can use linear interpolation, HF plus quality X times HG minus HF. And you can find these values from where? At 200 kilopascal. So let's go, let's see if we have table. Oh, we have the table right here. It's a pressure table at 200 kilopascal right here, 2 bar. HF is this number, 504.7. Hg is this number. So let me write them here. 504.7. Quality X is 0.6. Hg is 2706.7. HF is again 504.7. So you can determine H1. So if you do the calculation, H1 is 1825. Is that right? Oh, 0.84 kilojoule per kilogram. What about H2? We know it is saturated vapor. So where is saturated vapor? Right here, Hg. So H2 is going to be Hg because it is saturated vapor. But what condition? At 200 kilopascal. So at 200 kilopascal, Hg is this number. 2706.7 kilojoule per kilogram. What about this one? We have oops. Okay, there is a mistake here. The pressure table is 4 megapascal. The pressure at this point, it is not 0.4. It's a typo. It is 4 megapascal. 4 megapascal, okay? Sorry for the mistake. So at 4 megapascal, saturation temperature is going to be 250 degrees Celsius. However, the temperature at the inlet is greater than the saturation temperature. Therefore, the phase change process at the inlet is going to be superheated vapor. So H value at the inlet at 4 megapascal, 360 degrees Celsius, 4 megapascal, 360 degrees Celsius, H value is going to be this one, 3,117.2. 3,117.2 kilojoule per kilogram. Then we have everything. There's H in is this number right here. H2 is this number right here. H1 is this number. So we have everything but M1, M in, and M2. So what do we need to determine? We want to determine the mass of the steam that has entered. So M in can be found from these two equations. So basically, M in is M2 minus M2 minus 10 kilograms. So in other words, you can say M2 is M in plus 10 kilograms. Then M in plus 10 kilograms goes in to this M2. Then you only have M in this equation. So that's how you can determine M in, which is 21.46 kilograms. So this is the mass entering the system. What is the final temperature in the cylinder? The final temperature in the cylinder is going to be, we have saturated vapor at 200 kilopascal, 200 kilopascal saturated vapor. So the temperature is going to be saturation temperature, 120.2. So T at the final state number 2 is going to be T set at 200 kilopascal, so 120.2 degrees Celsius. So that's how you solve this problem. That completes chapter 4. Any question about this problem, or the material that we covered in chapter 4, or anything about thermodynamics? So we have two equations, right? And if you have two equations and you have two unknowns, you can determine that, right? We already know H in, H2, right here. Oh, this one is H1. So we have H1, H2, H in, and we already know M1. So we have everything but M in and M2. So you have two unknowns and two equations. So you can combine these two equations to determine M in. Oh, by the way, again, don't forget that there's a typo. It is not 0.4 megapascal. It is 4 megapascal. And the numbers in the figure, they are incorrect. So forget about that, okay? They are incorrect. The properties at the inlet is going to be 4 megapascal, 360 degrees Celsius. So this is how you solve the problems in chapter 4. I think we did solve more than 6 or 7 problems using the same energy balance equations. So I hope that these are sufficient numbers of problems. You can also redo all the problems in the PowerPoint and also start solving the problems in the homework assignments. And as we discussed last Tuesday, there's a spring break next week. So the homework due is going to be a week from next week. So 2 weeks from now, which is going to be the 14th, right? So 14th is the due for the homework assignments for this chapter 4. Okay. So that's everything about chapter 4, and we have a new chapter. Chapter 5. Chapter 5. I know that today is right before spring break, and the most of you are already pretty exhausted and want to have a fresh after spring break. But there's a good news, which is that chapter 5 is the easiest chapter in thermodynamics. So we can have a break and you can study. I can even finish the entire chapter 5 today, but I know that it may be too stressful. So I'm going to leave something for the after spring break. So what we are going to study is more like the fundamental of thermodynamics. So we will be more focused on the physics rather than mathematics in chapter 5, okay? So let's talk about the second law a little bit more. The second law means heat transfers from higher temperature medium to a lower temperature medium. So if I have this hot coffee and then place this coffee on this desk, the only heat transfer direction is from this coffee to the surrounding air. There's no way, the coffee can absorb heat from the surrounding air and becoming, the hot coffee again. That is only possible in a movie like Doctor Strange or something, right? in this chapter 5, we are going to study 5, the cycles. 5, the cycles. They are heat engines. They are heat engines and refrigerators and heat pumps. So we are going to study 3 systems: heat engines and refrigerators and heat pump. So we studied many thermodynamic devices in chapter 4. Now we are going to combine, the several thermodynamic devices to make a cycle. So we are going to study 3 different cycles. They are heat engine, consist of maybe a heat exchanger, or the pipe, and the in a refrigerator we have a compressor, heat exchanger, throttling valve, etc. So we are going to combine several thermodynamic devices to build a cycle, and we are going to study 3 cycles. They are heat engine, refrigerator, and heat pump, and which are pretty simple. And to understand heat engine, refrigerator, heat pump, we are going to use a new concept which is called thermal energy reservoirs. Thermal energy reservoirs are hypothetical bodies with a relatively large thermal energy capacity. One of the examples is that, if you want to build a power plant, you need to have a, the sustainable, the cooling sources. For example, the air, when we want to have an air cooling system, or, the water from nearby lake or river, so we can have a constant temperature, the fresh water to, to cool down our working gases. Those are considered as a thermal energy reservoirs. So the amount of, the coolant is too much. So even though I release heat into these thermal energy reservoirs, their temperatures do not change. Those are the concept of thermal energy reservoir. So basically, if we talk about, the power plant, so I'm going to build a power plant like this. I don't know what is the typical, the shape of power plant. So this power plant has a turbine, maybe. It may have a turbine inside. And there should be a, a generator producing electricity. And this turbine should be connected to a boiler that burns something. So there is a tall chimney producing this toxic gases. Not toxic, okay? Do not, release toxic gases into the nature. So we are going to add some catalyst converter to minimize these toxic gases. Anyway, and to remove any waste heat, we want to use a coolant, and we don't want to use a coolant from our tap water. We want to use this lake. So it's a lake. So we are going to pump this, the water from nearby river. So trying to, the cool down the, the working gas inside. So there's a cooling system goes in and out. And there is let's make something environmental friendly. Oh, it's a bio, the waste power plants. So we dump those, the trash. We burn them to produce heat. So we burn this one. So this is fire. Things are getting more, the complicated. It's campfire. So we generate heat and produce steam. So steam enters this turbine. So if we assume that we have enough trash, so we have the enough trash continuously, the people are dumping trashes, so we are burning them, then we can assume that we can provide heat, let's say heat transfer Q, which is at high temperature, into this power plant system continuously without any change in the the fuel side. That is an example of thermal energy reservoir. So we have plenty of the fuel. So even though we burn the main a lot of them, we still have the plenty left over. So we can continue providing them without any the intermittency. That is thermal energy reservoir. Similarly, we have plenty of water in this river. River is not enough. So let's make it it's a Pacific Ocean. So we have a lot of water. So even though the water enters at 20 degrees Celsius, and the observing heat from this turbine system, and the higher temperature the coolant is released to this ocean. However, since we have plenty of water, even though we dump the high temperature the water into this the ocean, it's not going to change the temperature of this ocean. So always we can the pump 20 degrees Celsius the water into the cooling system, even though we dump the high temperature heat later, because we have too much water. So even though we dump this heat into the system, it doesn't change anything. That is the concept of thermal energy reservoirs. So there are two temperature points. One is at high temperature. The other one is at low temperature, QL. So we are observing high temperature heat, produce power, produce work, W, and release waste heat into this ocean. This is what is called heat engine. Consists of two thermal energy reservoirs. So this is an example of heat engine. Okay. So this heat engine, which is right here, heat engine, HE, not heat engine, consists of two thermal energy reservoirs. One is at high temperature, the other one is at lower temperature. So one is at high temperature, the other one is at lower temperature. So high temperature is going to be, so we have a thermal energy reservoir, which is maintained at high temperature TH. Low temperature thermal energy reservoir, which is maintained at low temperature TL. So we are observing heat from this high temperature. For the amount of QH, by running turbine and generator, we produce work, W, but sometimes we need to consume some of the work that we produce. So let's say network. We produce network, and there should be waste heat that we need to remove by running cooling system, and we release waste heat to a low temperature thermal energy reservoir. So this is how heat engine works. So this one is this power plant system. So basically the idea is that we have plenty of fuel. So even though we release this QH to this heat engine, the temperature of this the thermal energy reservoir is not going to change. That is thermal energy reservoir concept. And here, even though we keep releasing, even though we keep transferring this waste heat into this thermal energy reservoir, because the amount of this thermal energy reservoir is too much, so it does not affect the temperature of this thermal energy reservoir, such as this Pacific Ocean. So if I, fly to, the Pacific Ocean, let's say, the San Francisco Bay Area, I have a hot coffee here, so I'm going to dump this one to the ocean. It's going to increase the Pacific Ocean temperature from 20 degrees Celsius to 21. No, it's not going to affect anything, right? So that is the concept. The thermal energy reservoir is like a Pacific Ocean. So the amount is almost infinite. So even though there is a heat transfer between, it's not going to change the properties of this system, properties of the reservoir. These are thermal energy reservoirs. So for the heat engine, we have two thermal energy reservoirs. The direction of heat transfer is from high temperature to low temperature. The difference between QH and QL becomes W net. So we produce W net from QH, and the remaining heat QL is going to be removed from this heat engine so that this heat engine can produce more W net. So that's what heat engine is about. So in this heat engine, we have two thermal energy reservoirs. One is at high temperature, the other one is at low temperature. And we use high temperature heat to produce steam to run turbine, and turbine to run generator to produce work. So we can produce work, W net, and we have a waste heat should be removed. Like we cool, our engine by using coolant while we are driving. So this is how it works. So the amount of heat transfer from high temperature thermal energy reservoir is going to be QH. The amount of heat that we reject into this low temperature thermal energy reservoir is QL. So if we apply energy balance, energy transfer in minus energy transfer out, it's going to be the change of energy of a system. In that case, heat engine is going to be steady state system. If you build a power plant, it should be steady state system, right? Have you seen a power plant that is unsteady system? I know two systems. One is called Chernobyl. The other one is called the Fukushima. Transient. Steady state. So that's what you need to be steady state. When you're driving your, the car, let's talk about this steady state a little bit more. When you drive your car, unless you have something, the brand new, the old ones usually have this giant gauge. One says, the 0, 1, 2, 3, 4, 5, etc. And it says RPM. The other one is 10, 20, and 3, and 30, 40, and 50, and 100, the 200 and 300, it says mph, right? And we usually drive it this way, right? No way, no way, no way. And there are two more gauges. One is like, the C and H, right? And what is the last one? E and F. Oh, this is the only time, many of the students like this letter F, right? No. So what is the most important gauge here when you're driving? What is the gauge that you need to monitor to make sure that you are safe? Okay, what is the risk factor? Let's talk about the risk. What happens if you drive in this way? The worst case is going to be, let's assume that there's no accident. I don't want to talk about any accident. The worst case is that you're going to pay, the fat ticket, right? Speeding ticket. So maybe $200 if you don't watch this one. Okay, not bad. Okay, 300. Okay. What about this one? The worst case happening is going to be You need to find the bucket and then walk to the gas station, right? That's the worst case. So nothing wrong. What about this one? Not much. You don't want to go there, and now you're going to hear some noise from the front, and you will push the brake. Have you watched this one? Not really. What is the how much that you're going to pay if something goes wrong here? If it hits like there, you should be very happy because you can buy a new car, right? This is the most important thing. So when the the needle is pointing right at the center, that means that you are running steady state, and it's going up beneath that the transient. You don't want to see your engine is running transient. Of course, in the warming up at the beginning, of course, the temperature is going to go up transiently because you just started your engine. So once it hit the steady state, it remains right there. So that's the same thing. When you run a power plant, you want to make sure that it's going to run steady state. If it's transient, meaning is that something goes wrong, either the boiler side or the cooling side. If the cooling side goes wrong, what is the one of the examples? The tsunami hit the Fukushima power plant, so it completely ruined their cooling system. So that's what all the tragic things happen, right? Anyway, when we talk about heat engine, refrigerator, heat pump, our main assumption is that we are talking about steady state operation, okay? What about refrigerator? Refrigerator looks similar to this heat engine, but slightly different. How many thermal energy reservoirs when you run a refrigerator? Think about your house. You have a refrigerator, right? You don't? You should have one, right? To be healthy, right? You don't want to eat something smelling, right? So how many temperatures are present when you run a refrigeration system? Of course, inside the refrigerator should be maintained at low temperature, right? That can be considered as one thermal energy reservoir because it will maintain constant temperature, right? And another temperature is going to be outside of the refrigerator where heat is going to be dumped from the refrigerator. So we have kitchen air temperature and the temperature of the refrigerated space. So the temperature of the refrigerated space is going to be TL. The temperature outside of the refrigerator is going to be TH. So this one is kitchen air. This one is refrigerated space. What is refrigerator? Observe heat from outside and pump that into inside. So your milk can go bad as fast as you can, right? No, that's not the way. We want to observe heat from the refrigerated space and release that heat to the outside, the kitchen. But when we talk about the second law of thermodynamics, is it okay? In the previous example, heat engine, we observe heat from high temperature because heat transfers from high temperature to low temperature. So if you look at the heat transfer direction from top to the bottom, the heat transfer direction is from high temperature to low temperature, which is reasonable, which is not against the second law of thermodynamics, so we can produce work. But what about here? Heat transfers from low temperature to high temperature, which is uncommon, which is against the second law of thermodynamics. So it doesn't happen naturally. To make that happen, we need to sacrifice. What we need to sacrifice? The electricity bill. We need to provide work to make that happen. So that's why, this one, we can produce work because this can happen. This is not against the second law of thermodynamics, but this is against the second law of thermodynamics. So to make that happen, we need to put some energy into that. That is W net. What is heat pump? Heat pump is a heater we use in winter to, to heat a house, right? So how heat pump works? It has two thermal energy reservoirs. One is low temperature. The other one is high temperature. Low temperature is going to be outside. Outdoor. High temperature is going to be indoor. So what heat pump does, it observes heat from outside, release that heat into a house. So it observes from heat from outside and release that heat into inside. So is it common? Is it okay with the second law of thermodynamics? Heat transfer from low temperature to high temperature. No, it is not okay. So this is not going to happen easily. So we need to provide work. Now let's compare. If you look at this refrigerator, if you look at this heat pump, are they the same or are they different? They look the same, right? So heat pump is actually a refrigerator. Do you have a heat pump in your house? Or just conventional heater or heat pump? Conventional heater or heat pump? No idea? Okay. The heater looks giant or small? Oh, okay, okay. So let me explain, how this heat pump works. It's pretty simple. That you can build a heat pump today when you go home. So let me tell you, how to build a heat pump. So this is a house. I'm not good at painting, so this is the door. And now the first thing you need to do is that remove the door, destroy the door, and move your refrigerator and place right in front of the door, facing outside, so the door opens this way. It's not, the expensive refrigerator. Expensive refrigerator opens like that, right? This one's one side, right? So this is not very expensive, so don't worry about that, okay? Now you destroy the doors. And there's a power. Usually there's a power near the door, right? And plug in. Now you have a heat pump in your house. So let's see how it works. What this refrigerator does, it cools down inside, right? But thermodynamically, it's not cooling down. It is absorbing heat from inside, right? It is absorbing heat from maybe milk or steak or vegetable inside the refrigerator. So what happened is that it observed heat from outside. Q, L goes in. And can you destroy the heat? You cannot create or destroy energy. It is not possible. You can only transfer energy from one to another location, or you can only, convert one form of energy to another form. So this heat should be removed from the refrigerator to where? Inside the house. What is the temperature inside? Oh, maybe 20 degrees Celsius. Outside, 0 degrees Celsius. It's winter. Freezing. So how can I don't know how to do that. Making this color looks freezing, right? So this heat transfer from low temperature to high temperature, it's against the second law of thermodynamics. Naturally, heat transfer should be from high temperature to low temperature. So it is not possible naturally. So to make that happen, we need to provide what? W net work. So this is heat pump. So if you have a heat pump installed in your house, you have a giant refrigerator, and then you are cooling the world. Sounds interesting, right? So if you install, if you make a new heater like that, what do you think about this one compared to conventional heater? So let's talk about conventional heater. So I'm going to install, the conventional heater. So plug in. So I'm going to, so there's another, the power, the plugged in. So it is working. So it consumes, the electricity to generate heat. Which one is more efficient than the other? Running a giant refrigerator or just electric conventional heater? So which one? This one is A, this one is B. So which one is more efficient? A or B? You have a 50% chance. Probably B. What do you think? What do you think? Okay. The answer is this one is more efficient. Let me tell you why. It's pretty simple to understand. So when you buy your, the heater, let's say you go to Walmart, you buy a, the small heater for your room, and what do you want to check? Price, of course, right? And the next thing is gonna be, what is the, what is the power? What is the rating? So if it is 2,000 watt heater, that means every second it's going to consume 2,000 joules of, the electricity. So if you spend 2,000 kilowatt, let's talk about something simple number. If you spend 100 joule of electricity, how much heat this one can deliver? What is the efficiency of heater? What is the efficiency of electrical heater? The maximum efficiency is going to be 100%, right? What is the efficiency of electrical heater that you can buy anywhere? It should be, what is the last form of energy? What is the waste form of energy? Electricity, heat, or mechanical energy? There are many things. What is the waste form of energy? Heat, right? That's correct. So generating heat is the easiest way you can do because that is the waste form of energy. So if you consume electricity, what is the last form of electricity? Heat. So what is the efficiency of heater? Always 100%. It should be 100%. If it is 90%, what happened to the 10%? What happens to the 10%? It's a rebate. You return back to the electricity company. No, if you consume 100 joules of electricity, it should be there, and maybe it can be another form, and eventually it should be heat. So if you consume 100 joules of electricity, you will get 100 joules of heat. So what is the efficiency of a heater? 100%. So if you go to Walmart or Target and say that, oh, this heater is very efficient, that's correct. Every heater is very efficient because their efficiency is always 100%. So if somebody say that, oh, this heater is more efficient than this heater, which is incorrect, because they have the same efficiency. Because you're converting useful, valuable energy, which is electricity, to unuseful, useless form of energy, heat. So you're converting good thing to a bad thing, right? So the efficiency of a heater is already 100%. Gas heater is a different story because it depends on, whether it is complete conversion, complete combustion or incomplete combustions. So there are, the multiple factors involved. However, if it is electrical heater, the efficiency is going to be theoretically 100%. So if you consume 100 joule, what is the heat that we can get? 100 joules of heat into the house. So 100% efficiency. Let's talk about this refrigerator. Let's use the same electricity. So I'm going to consume 100 joules of electricity to run this refrigerator. So what this refrigerator does, it absorbs heat. So how much heat? Let's say maybe 100 joules of heat absorbed from outside. So what happened to this 100 joule? Make it disappear? No, it heats up the house, right? So 100 joules goes into the house. Oh, wait, we consumed 100 joule of electricity. What happened to this one? Right. So you consume 100 joule, and what is the heat you deliver to the house? 200 joule. Make sense? Right? Makes sense? So having heat pump is more efficient than conventional heater. Having giant refrigerator and remove the door and placing them outside, make your neighbor look at you, the stupid, right? It looks very stupid, right? However, it is very efficient because you are going to consume electricity that becomes heat, and you're absorbing heat from outside that becomes heat into the house. So you're only spending 100 joule, but you are actually delivering more than 100 into the house. So the efficiency-wise is going to be always greater than 100%, because even though the refrigerator is pretty old and it cannot absorb as much as before, maybe 1 joule of the heat transfer into the house, you still have 100 joules of heat from the electricity. You have this one on top of it. So it is always higher efficiency than 100%. Interesting, right? Then why doesn't every house have heat pump? You said you don't have one. You have a conventional heater. Why is that? Because you are building giant refrigerator for the size of your house. So it's going to be expensive. So the capital cost is much higher than the conventional heater. So that's the reason. But that's the reason from the the business point of view. There is a reason from engineering point of view. So let's talk about this heat pump. One is installed in Michigan. The other one is installed in Texas. What is the difference between Michigan and Texas? It looks like Michigan, Texas. No, Michigan, Texas. What is the main difference? It's hard. The sun is killing people already, right? It's not hard. So we survive. The main difference is that what is the temperature outside, in Texas in winter? Not very low. What is the temperature outside in Michigan? Pretty low, right? So when you have a heat pump in Michigan home, when you have a heat pump, in Texas home, which one is more efficient than the other? They're not the same efficiency. Which one is more efficient than the other? Think about this refrigerator point of view. You are the refrigerator, cooling outside. Which one is easier than the other? So outside, let's say, outside temperature is going to be, in Michigan, outside maybe minus 10 degrees Celsius. Oh, it's very cold. Texas is not that cold, maybe 10 degrees Celsius. So which one is easier to cool? That's correct. Because the temperature outside is not that low. So cooling this one is not that it's not that difficult. However, in Michigan, the temperature outside is already very low. So if you want to cool this outside, you need to, it's gonna be a little harder than Texas. So when you compare the efficiency point of view, Texas is more suitable to have a, the heat pump. That's why, the many of, the Michigan homes do not have a heat pump because it's not that efficient as the southern area. But if you go to the southern area, you see many homes have, the heat pump because, the heat pump is more efficient. However, there's a fundamental problem in this analysis because I'm comparing heat pump and electrical heater. What is the heater in your house, if I may ask? Is it electric heater or, I mean, the heater to heat your house? Is it a gassy heater or, right? Electric heater is more expensive than gas heater because gas price is much lower. So if you compare heat pump and electric heater, this one is more efficient because we are talking about the same price electricity. However, gas price is usually lower than electricity. So if you compare heat pump and gas heater, it's not easy to compare. It depends on the gas price and also the temperature outside. So when you have a heat pump in your house, I have a heat pump in my house. So, and my thermostat has two options. You want to use a heat pump, then this one, or you can use a gas heater. So usually heat pump in Michigan area, they have a two parts. One is a gas heater. On top of it, there is a heat pump. And usually when outside temperature is very low, they don't run heat pump because cooling outside is not easy. So instead, they run gas heater. When the outside temperature goes up, but still the temperature is not hot enough, so you need to run the heater, then use a heat pump. So you usually set, the threshold temperature, let's say 5 degree or 10 degree. Above 10 degree, run the heat pump. Below 10 degree, run the, the gas heater. Because, it depends on the cost of the electricity, right? Make sense? Sounds interesting, right? So these are the three systems that we are going to study: heat engine, refrigerator, and heat pump. And each of them, that has many thermodynamic devices inside. Let's say heat. This one, it has a heat exchanger, so we can, the transfer heat from high temperature thermal energy reservoir to the working gas inside the system. It's going to be steam. And there's a turbine to produce work, and in this case, compressor and etc. So in chapter 4, we studied each thermodynamic devices, how we can analyze each of them. In chapter 5, we are going to combine them and say this one is a refrigeration cycle, this one is going to be heat engine cycle, this one is going to be heat pump cycle. So we are going to study these three cycles. That's what we are going to study in chapter 5. Make sense? Okay, we have 8 minutes, so let's stop here since we have a spring break. So at least you got the idea what we are going to study in chapter 5. So the most important thing is to understand how heat pump works, how heat refrigerator works, how heat engine works. The actual mathematical, the calculation is going to be much simpler than, the previous chapters. So there will be not much difficult things, to do after the spring break. But more important thing is going to be how to understand the heat transfer phenomenon in each cycle. That's going to be the key, even though the solution is going to be easy. So, what you need to focus on to study this chapter 5 is going to be how these cycles work, in the physics domain, not the mathematical domain. Okay. All right, that's everything. And, I hope you enjoy spring break and see you, later after the